In the previous video, I spent a lot of time talking about LiDAR, about how it's processed and how it was collected. In this video tutorial, I would like to cover a little bit more about other collection methods that I've kind of really generically grouped into survey base maps. And if you recall, LiDAR is something that's collected over a very large area. The points are not strategically placed. The spacing is between 1 to 2 meter resolution. And then I said that survey base maps, the point spacing can vary in resolution and points are usually strategically placed. And this is dependent upon the survey method. So that's what I'm going to focus a little bit on, is the second category, which I kind of called survey base maps, really generically and vaguely. So what is surveying? Surveying is a discipline encompassing all methods of measurement, processing, and dissemination of information about the physical earth and our environment. Because we will work a lot with base maps that come from surveyors, we should probably know something about what surveying is. So there's a definition. And then here's some interesting dinner time facts. Surveying seems to have originated in Egypt. The earliest recordings were that of Sesostris about 1400 BC, who divided the land of Egypt into plots for the purposes of taxation. In that day, they were called rope stretchers. They weren't called surveyors, because they used ropes with markers to measure distances. Geometry later came about. A Greek person by the name of Heron applied science of geometry to surveying about 120 BC. He also authored the Dioptra, involving methods of surveying a field, drawing a plan, and making calculations. And then later there's some significant contributions that came from Frontinus, a Roman, who wrote several essays documenting methodologies. And of course there are a lot more individuals who made significant contributions, but these are the only three that I remember. And then there's surveying measurement tools. So I talked a lot about LiDAR, how there's an aircraft involved, and some lasers and all that fancy stuff. Well, here I'm going to talk about some different types of tools, and they're kind of grouped together into broad categories here, and I have kind of 9 major categories, and I have a 10th one, which is classified as other. And the reason why we have an other category is because as technology continues to advance, so does the surveying tools. So today these may be the surveying tools, and tomorrow it may be a completely different list here. There are several tools available, so we're only going to name, of course, a very small handful here and group them into major categories by method. So we have pacing, and of course it's just walking and counting, odometer readings, optical rangefinders, and these are also used in LiDAR data collection, tachyometry, which is stadia, subtense bars, taping, electronic distance measurement, inertia methods, which is also used in LiDAR collection, satellite systems, and then other methods. And the ones I put asterisk next to, these are the most common methods that you're going to encounter. So I'm going to talk a little bit about electronic distance measurement, and these for short are called EDM, because these are the ones that you're going to encounter the most in landscape architecture, other than LiDAR data. So total station instruments measure the distance and direction simultaneously and transmits the results automatically to a built-in computer. The output data file is very similar to that of a LiDAR LAS file. Point numbers, XYZ coordinates, point classification, and other information can be outputted from the total station output file. We'll actually look at an example of one of those later. So let us consider this very crude sketch diagram. This is actually a sketch of my yard. So we have a main house structure over here, and then we have a garage. It's actually a detached garage, but you can't tell from the way I drew it. Have a tree in the front yard, a tree in the backyard, and this whole yard just gradually slopes down towards the street here, towards this ditch. And it's not a significant slope, it's real gradual. I'd say between maybe, I don't know, 3 to 5% slope. It's just real gradual. Except right about here we have a retaining wall, and the retaining wall is about 4 feet tall. We have another retaining wall here which is about 4 feet tall, which allows for a walk-in basement. So this area in here is pretty flat. We have a little pond area here that kind of drains out over here, which collects some storm water. We have a little mound here because I have my septic tank dug up, so there's just a little dirt mound going on here. We have some steps that go up into the structure. We have a driveway. And I don't really have a curb situation, but I'm just gonna draw one in here just for the purposes of discussion. And then I have a little pipe that goes underneath my driveway, and it's not nicely formed like this. It's just a dirt mound, but for the purposes of discussion, I'm just gonna put a nice concrete daylight thing going on here, and the same thing down here for this southern one. So let's take a look at what LiDAR data might collect from this. So if we recall, LiDAR data is going to space the points about 1 to 2 meters apart, and we're going to say maybe this is 2 meters apart or something along those lines. So it's going to be a regular pattern like this. Every so often there's going to be a dot, and it's going to sample the elevation. Now of course if I go to build out this terrain, I'm not going to see my curb information. I'm not going to see my ditch information, or the fact that I have a mound in my front yard and a pond on the side, or the fact that this is over here, this is kind of lower. We might get this lower area here because the point just happened to hit this area right here. But we won't know that there's a retaining wall here because there's not a point over here. The next closest point is all the way over here, so it might just say that this is just a gradual decrease here in terrain. And this simply has to do with because of the fact that this is the point resolution. Now if we use the EDM method where we go out there with the total station and actually collect data, we have total control over what we sample in this landscape. So we may decide, okay, let's go out and let's get each of the corners of these buildings, the elevation of each of these corners, the elevation on the top of this retaining wall and the bottom of this retaining wall at strategic points. Same thing over here. While we're at it, we'll get the elevation of the pond. We'll maybe get the major drainage line. Maybe we'll do the same thing with the ditch, top of the ditch, the middle of the ditch, the bottom of the ditch. Maybe we'll also get this curb information over here and this driveway. So when we go to build out this terrain, it's going to be very, very detailed. We're going to see that over here it's really high and over here it's really low. There's a mound here in the front because this was sampled. But if you recall, with the LiDAR we're not going to get that because that's the best point resolution that we can get. And of course, you know, the technology for LiDAR is getting better and better and better, so this may not always be the case, but right now this is what the case is. So there may be instances where you'll have to use this electronic distance measurement method to collect data, and this is going to be the most common method for smaller scale sites. Well, how you're going to get your data is in this EDM method, using this EDM method. Point processing terrain representations. Points can be processed into different terrain representations. Many mathematical algorithms exist today to create different terrain representations from points. We will explore each of these in varying detail. So patterns can be identified in point layout and then connected. The points can be connected together using computer software programs such as Civil 3D or ArcGIS to automate the process to create different terrain representations. So let's take a look at some of these different terrain representations, and we're only going to take a look at 3 of the most common terrain representations, and of course there's others. The first one is the tin. So if we connect 3 points within close proximity, we can create what is called a triangulated irregular network, which is also called a tin. So it's just abbreviating triangulated irregular network to create the word tin. So we can see from this diagram on the left side we have a bunch of points. The points are connected to create this tin. And when you create this tin, what you end up doing when you connect 3 points is you create what they call a face. And a face is actually a plane. You have enough of these faces connected together, enough of these faces built, enough of these points built, and enough faces, you create a surface. So it actually looks like a 3D surface. So to create a tin, something called the Delaunay triangulation is used. And this is actually a mathematical algorithm that was developed by a guy named Delaunay to connect these, you can call them, kind of connect these dots together. So what they do is they take a point and they create a sphere, and the sphere will expand out so many times until it hits a point, and then it'll expand again until it hits a second point, and when it hits 2 points, so it'll take the first point, it'll expand from that until it hits a second and a third, and now it has 3 points contained within the sphere, and it will connect those 3 points together. And of course there's a lot more going on in the algorithm than just that, but for the purposes of this demonstration, that's all we really need to know. So tins are most commonly used to calculate volumes, especially between two surfaces, such as existing and proposed. So this is going to be pretty useful to us when we have to calculate earthwork, cut and fill. The next most common form of terrain representation, especially when working with construction documents and needing to communicate your design, your terrain design intent to contractors, is the contours. So how these contours are created is integer value points in between points with decimal values can be created. So we can see in this example, we'll say that along here these are whole numbers. So for example, maybe for whatever reason this point here is 101.33675. And then this point here just happens to be 102. And maybe this one here is 103. And maybe this line along here is 104, and this line along here is 105. Just hypothetically speaking. So what it does is it can sometimes create a point in between where it thinks from here to here is this elevation value, and it'll create a point there. And it'll do the same thing along here, and I didn't draw on the points here. It'll create a point, it'll try to interpolate where this contour needs to be by creating points. So once the integer value points are created, then the integer value points can then be connected to those with similar z values or elevation to create contours. And that's what we see here. So along this line here are points, which of course are connected with contour lines of equal elevation. So one thing that you could say about contour points is that they're coplanar. The third most common form of terrain representation that you can expect to find are those that ArcGIS uses the most, and that is the raster. And we can probably recall this from earlier tutorials. A raster is essentially a grid pattern which can be created overlaying the entire area. Each grid cell takes on a color depending on the elevation of the point contained within. And then this representation is called a raster, such as those that we have used in ArcGIS. So there are several actually very different ways to artistically represent terrain, which we'll explore much later. So I do want to mention, regardless of which terrain representation you choose, most software applications are going to use points as the most basic building block to build terrain. So for example, if we fed Civil 3D a set of contours, as soon as we try to do something with it, such as build a surface, it's always going to convert those contours to points and then build the surface from that. If we give Civil 3D a surface, it's going to convert that surface to point before it produces contour. So it's always going to go back to that basic building block, and of course if it doesn't exist there, it will try to create or interpolate. So why is all of this important? We talked a lot about LiDAR, and we talked a lot about points and surveying. And the reason why is because as landscape architects, we will need to create one or more of the following terrain conditions. we'll need to create a level area to put something on. We'll need to create a circulation way level enough to travel on. We'll also need to create maybe some special effects to solve some special type of problems, like drainage or maybe some sort of visual problems, something along those lines. So all of these involve a process called grading. Grading is the act of remodeling the landform. So your design will sit on a terrain base, and you will have to sculpt this terrain base so that your design is somewhat feasible. Of course, you want people that come in from the parking lot to be able to get to your building and not have to cross a ravine or something. At the 2013 Geodesign Summit in Redlands, California, someone summed up my design process very beautifully. And as I think about it more, this is exactly what I do, but may not state it exactly like this. So one guy at the Geo Design Summit basically said that when he designs, he thinks of going in to get his hair cut. And of course, this guy doesn't have very much hair. So it makes it very, very interesting and very easy to remember. So over time, through experience, you will learn these three very fundamental design process concepts, which can be applied to more than just grading. When designing or grading, you want to create a design or grading plan that will, and in this order, first protect what you have. So this often involves an extensive site analysis and a very intimate understanding of the site conditions and how each system works together to support the other. When I'm talking about system, I'm not talking about like storm sewer or anything like that. I'm talking about both people systems, hydrologic systems, the natural community type systems. I'm talking about systems in a very generic sense. And we want to assess the strengths, the weaknesses, the opportunities, and the vulnerabilities. And we want to look at these in great detail. So like the guy at the Geodesign Summit, he was looking at this in respect of his hair. He wants to protect what he has. Secondly, he says to edit, and edit carefully. So edit existing conditions. After learning about the site, you can now make informed decisions about what needs to change for the better. By now you can see what works and what does not, and how these things affect different communities, both human and non-human. And then thirdly, he says, after you protect the little hair that you have and edit carefully, then you may have to do some inventing. So sometimes you will need to make major changes, and this will have, of course, the greatest impact. So if you're going to grade, then grade. Do a good job. If it's worth doing, then do it well. So growing up, I grew up in an Asian home. One very important concept we learned at a very young age is if you're going to do something, then do a good job. Otherwise, don't do it. The impact from doing a bad job can be much worse than what it was from leaving it alone. The time and money needed to clean up the mistake can also cost more, almost exponentially, compared to the original cost of construction. And some damage cannot be undone, such as the death of wildlife community that may have once lived in the now destroyed riparian habitat. So remember, protect, edit, and invent. And it's kind of interesting how this person related this to his hair loss. This was something that was obviously very precious to him. When we design, we should also relate design to something precious to us, so we will not carelessly design. So it's very easy when you're designing to kind of disassociate yourself from the site and the different communities that live there. And we don't want to do that. We want to make sure that everything that we're doing, we imagine ourselves we're going to have to live there, and maybe we have to live there for the rest of our life. So we want to be very, very careful when we design or when we grade. So in summary, I've covered some LiDAR, gave you an introduction of LiDAR, how it's collected, how it's processed, and what all the different terminologies associated with LiDAR means, and with digital terrain modeling also means. I gave you an overview of the different surveying methods and what they're called and how they're grouped up. I also discussed three major terrain representations. I talked about the tin, the contours, and rasters. And then I also talked a little bit about how to grade or design. You want to protect, edit, and invent.